Okay, welcome back. It's 15.4 Green's theorem, which is a pretty cool theorem. It relates the area inside of a closed curve to the line integral around that curve. Okay, so there's a weird relationship between the line integral of this curve C and the double integral to find the area inside of that curve. Okay, so in particular, we have theorem 15.8. Okay, given some nice conditions that hold, we'll have that the line integral of a vector field f on the curve C, here given in differential form, is equal to the double integral of this difference between these mixed partials. Okay. Note, if this thing's conservative, it's going to equal 0. And that's clear from our equivalent conditions given last time. The conservative is the same as line independence, and also any line integral on a closed curve will be 0. Okay, but you could really see it here because if the mixed partial, if it's conservative, those guys are going to be the same, and so that will be 0. Okay. Anyways, the proof is kind of a neat thing. They only prove it for some simple cases. So let's say this is kind of like not a perfect proof, but kind of more of a sketch of a proof. So we have some region, and we have two kind of simple curves like this and this. We'll say this is y equals f1 of x, and maybe this one is y equals f2 of x. Okay. Let me make sure I get the orientation and stuff right. So I want to go forward and then backwards on that thing. Okay, so what you're going to kind of do is just take a piece of Green's theorem and show it's true, and then take the other piece and show that's true. So the piece we want to start with is this line curve of m dx. And so recall that m is some function of x and y, right? It's from this vector field f, which is equal to some m of x comma y comma n of x comma y. So to evaluate this piece of this integral on the first curve, maybe we should do f1 and then f2. Let me see what the book does. Yeah, they go f1 on the bottom. So let's make the bottom guy f1. Oops, do it again. Okay, so for that bottom curve, what are you doing? It's going to be m of x comma f1 of x dx, and then we add it to the other one, right? So let's clear that and just make this represent the entire curve. So for the second part of the curve, so this bottom one is C1 and the top one is C2. Then you'll have, so that would be C1, and then plus the integral of C2 m of x comma f sub 2 of x dx. Okay, and right. So you can parameterize those so they go from the first guy is going to go from this point, maybe it's A, to this point B. Okay, so I'd have, long story short, you're going to be able to take these two integrals and turn them into one. So you'd have m of x comma f1 of x dx plus m of x comma f2 of x dx. I'd rather put the dx totally at the end of all that, from A to B. Okay. And then we're going to take that thing and compare it to the other side. And in particular, we want the partial of m with respect to y. Okay, so we're kind of comparing this piece to this piece over here. Okay, so the other piece then that we're comparing it to, the double integral of the partial of m with respect to x over this region. okay, with respect to y, not x. Got a 50-50 chance I screwed it up. dy dA. Okay, so in this case, I'm going over this region, so I'm basically, if you think of it, dy and then dx, I'm going first from the curve f1 to the curve, secondly to the curve f2, and then I'm integrating from a to b. And you kind of see you're going to get the same thing as what you got from the integral of m dx, right? So this guy, the integral of this portion with respect to y just give you m, so you get m evaluated from f1 to f2 dx. So that's just going to be the integral of m of x comma f2 minus m of x comma f1 of x, if you want to put x in there if you want to, f1 of x dx from a to b. And you see you basically got this sort of the same thing, but there is this issue with a negative, right? The negative will come up when you consider that the second integral right here, because technically the first integral we're going to have go from a to b, and then the second one goes from b to a. If you remember Calc 1 really well, to get them both going from a to b, what you do is just kind of, and I guess I screwed that up, you kind of put a minus there, and then that will flip the limits on the integral from b to a to b. Okay, so you get both integrals going from a to b, and then you can combine those together. I guess that was kind of what I was waving my hands about there. But ultimately, they are equivalent, okay, sort of. You see that they're still kind of backwards, but that's why that portion has a negative on it. So if you look back at our formula, it's not that this m dx equals the double integral of the partial of m with respect to y, it's that this equals the negative of that. Okay, so that's why those are kind of have reverse signs. Anyways, long story short, you do the same thing with the other portion, the n dy and the partial of n with respect to x, and show that those are the same, and it all works out. Okay, so yes, it works. It's a crazy thing that you can get basically the same information by looking at the curve as you can from looking at the area. Okay, so in the beginning, you're basically just applying the formula. Use Green's theorem to evaluate the integral. So let's one thing that does come up, you may need to know the area of an ellipse. So if you have x squared all over 9 plus y squared all over 4 equals 1, that's an ellipse. 2, 1, 2, 3, 1, 2, 1, 2, 3. What is the area of that? Does anybody know? It's just going to be 3 pi times basically the two different radii, like radii 1 times radii 2. So it'll be pi times 3 times 2, which is 6 pi. Okay, so just by the way, you may need that for some of the problems later on. Just want to make sure it's in your notes somewhere. Okay, so anyways, let's try number 3, I suppose. Use Green's theorem to evaluate y minus x dx plus 2x minus y dy. Remember, this is m, this is n. When we get to, it'll be the partial of n with respect to x minus the partial of m with respect to y. Okay, all right, so the path is the boundary of the region inside the semicircle. Y equals 25 squared minus x squared, so that's a circle with radius 5, so inside there. And outside the circle with radius 3, so this other circle with radius 3. So I need this region here, kind of in our double integral. So when I convert to the double integral, originally it's the boundary, so it'd be going around this thing, and wouldn't that be a nightmare? You'd have 4 different integrals, parameterizations all over the place. It'd just be a nightmare. So it's way easier to go to a double integral and just figure out the area of that, work with the area of that region. You still need this integrand, which is the partial of n with respect to x, which will be 2, minus the partial of m with respect to y, which will be 1, dA. Right, so we'll go to polar coordinates. It's clearly the best way to proceed on that one. 2 minus 1 is just 1, and then of course we have r, dr, d theta. I'm going from r equals 3 to r equals 5, and then from 0 to pi, and that should get the job done, right? So it's going to be the integral of r squared, evaluated from 3 to 5, d theta. That will be 25 minus 9, which is 16. Integral d theta. So it's going to be 16 pi, right? R squared over 2. So that's a mistake there. So that should be 8. So it'd be 8 times theta evaluated from 0 to pi. So that would be 8 pi. Okay, there it is. Let's do another. Some of these are pretty easy. Oh, this one kind of looks nasty, but it's not. So number 6, use Green's theorem to integrate this line integral, x squared minus y squared, dx plus 5xy dy. Okay, eventually I'm going to need partial of that with respect to x, which will be 5, minus the partial of this with respect to y, which will be 2y. Okay, and that will be inside my double integral over this region, which is some weird polar region, right? Okay, so the polar region is r equals 1 plus cosine theta, and that is a cardioid of some sort, right? So in the r theta plane, here is cosine. Cosine looks like this, and then 1 plus cosine will just shift that up 1 unit, so it'll look like this. And then when you go to your polar to the xy, but using polar coordinates, it's going to start at 2, and then at pi over 2 it'll die down to 1. And then at pi, it'll die down to 0, and then it'll increase back to 1, and then increase back to 2. So you get that object. You want to find the area, or you want to integrate that thing by integrating over this area. Okay, so that's the region we're integrating over. Okay, so anyways, I'm going to go to polar coordinates, so this will become then the double integral of 5 minus 2 times y. Y will be r sine theta, right? Let's totally make sure this is correct, right? So I mean the partial with respect to y is 5, partial with respect to x. It's partial. No, the partial with respect to y to x first. So I lost. It's not 5. So it's a partial of n with respect to x. That would be 5y. Okay, there's. I'm glad I checked. And then the partial of m for money in terms of y is negative 2y. Okay, so this that'll be right. So it'll be the integral of 3y. Okay, so that's 3y. Y is r sine theta, and then it's r dr d theta, so it'd be r squared dr d theta. And then I'm going from 0 to 1 plus cosine theta, and then from 0 to 2 pi. All right, so what am I going to get? R cubed over, when I integrate with respect to r cubed over 3, so that factor of 3 goes away, and I just have an r cubed sine theta, evaluated from 0 to 1 plus cosine theta d theta. Did I give you a video quiz yet? Is this the video quiz? Did I already give you a video quiz? I don't think I did. I will here. I won't make this one the video quiz. So I've already started it. All right. So this will be equal to the integral of 1 plus cosine theta cubed sine theta d theta. Do not cube that out. You want to do a u sub for 1 plus cosine theta. So du will be negative sine theta d theta. So this will be negative integral of 1 plus u cubed. Sorry, u is 1 plus cosine theta, so that would just be u cubed. So u cubed du, so that would be negative u to the 4th, so 1 plus cosine theta to the 4th all over 4, evaluated from 0, I think we said to 2 pi. And then that's going to be plugging in 2 pi, cosine of 2 pi is 1, so you get negative 1/4 minus, it's 0, the answer is 0. Okay, well there it is. It was a closed curve, so I should have been suspicious of that. But no, I couldn't be, it wasn't conservative, right? It wasn't an issue of being conservative because the mixed partials didn't equal each other. It would have been, you would have had a cancellation here. Okay. Let's do a video quiz for the next one. So number 7 is the video quiz, last quiz in video quiz set number 9. So we only have one more video quiz set left, video quiz set number 10. Anyways, this is problem 7 and WebAssign. Okay, so use Green's theorem to evaluate this guy. You can already see the answer. So x squared plus y squared is equal to a squared is what we're the curve we're worried about. Okay, so I need my double integral over that region, which is a circle with radius a. The partial of this with respect to x is negative 2e to the x sine of 2y. The partial of this with respect to y will be negative e to the x sine of 2y times 2. Okay, and then we'll have all of our material dA. It's not a nice cancellation. I was hoping that would just cancel to be 0. Did I take the derivative correctly? Derivative of the second guy with respect to x. It's just the derivative of e to the x is e to the x. The derivative of the first guy with respect to y, e to the x negative sine 2y. Yeah, I mean it's right. All right, well, whatever. So I get the double integral of negative. There's no way. I must have made a mistake. Hold on. Let me pause the video. I see what I did wrong. So the formula has a negative already in it, right? So it's always the double integral partial of m with respect to the partial of n. There it is. N with respect to y minus the partial of m with respect to, no, it's partial of n with respect to x. Sorry, minus the partial of m with respect to y. See, that minus is already in there, so this will be plus, that'll be 0, so that'll be a big 0, and it'll equal 0. Okay. Sorry about that. Okay, so, yeah. Anyways, there's that. Let's see what else they have. Green's theorem. Calculating work with Green's theorem, conservative vector fields. Oh yeah, so the line integrals for, you could use a curve, you could find, okay, so let's make this section 2. Using a boundary to find area. So imagine you can walk around the boundary of some farm land. You're trying to figure out how much area of farm you have. You can figure it out by just walking around the boundary. Supposedly, you figure out how much area you're dealing with. And it comes from making sure that in your double integral that your difference, let's see if I get this formula right, the difference between the partial of n with respect to x minus the partial of m with respect to y, you want that thing to equal 1, right? Because if that thing is equal to 1, you're actually just finding the area. Okay, so in order to pull that off, there's a couple choices you could use. The book is going to say use the following. So let the partial of n equal, with respect to x, equal 1/2, which implies that your big N will actually equal 1/2 x. And then your partial of m with respect to y, they say let that equal -1/2. So your big M will equal -1/2 y. Okay, so in your line integral, you have 1/2, or usually it's a equals m dx plus n dy. Doing substitutions, let's not call this, well, yeah, it is kind of area. So doing substitutions, you'll have m, we said, is -1/2 y, then dx, plus n is 1/2 x dy, and then rewriting it like they have in the book, factoring out the 1/2, you have 1/2 integral of x dy minus y dx. And you could use that to figure out volume. Right? So some of the problems in the book then will have you do that. Use the line integral to find the area of like a circle. Okay, sounds nuts, but you could do it. So let's try number 11. The area is from this x squared plus y squared equals 36. Okay. All right. So I'm going to go ahead and parameterize this thing. So we go r of t equals 6 cosine t comma 6 sine t, and then our area will equal 1/2, and with the t value we want to go from 0 to 2 pi, and then x will be 6 cosine t dy, the derivative of that will be 6 cosine t, and then minus y. So whoops, that's not y, this is y. So minus y, 6 sine of t times the derivative of x, which would be -6 sine t, right? Okay, dt. It's kind of it's more of a parlor trick at this point. But anyways, you have 1/2. This will be 36 cosine squared t plus 36 sine squared t dt. You can factor out the 36. Cosine squared plus sine squared is 1. So you're just getting 18 integral of dt. So that'd be 18t evaluated from 0 to 2 pi, and that would give you 36 pi, which is what you would have got if you just used pi r squared, right? This last one is the one where you have to use that formula for the ellipse in a circle. So let's try it. The boundary of this thing is a little bit weird, I guess. You would have to kind of go from the ellipse to the circle and the circle to the ellipse, so there would be some kind of intermediate line in between the circle and the ellipse. But in the overall integral, the line integral, those two guys would cancel each other, because the line integral in one way is equal to the negative of the line integral going in the other way. So that those parts would cancel, and basically you just have to figure out those two line integrals. Okay, we're not going to do the line integrals course because that would be annoying. We're just going to convert into a double integral. So we'll just do this one, and then we'll I'll let you go. So we have 3x squared y plus 8 dx plus x cubed plus 8x dx, dy. Okay. There's two curves here. There's a circle with radius 2, and then there's an ellipse that has 2, 3, it's 4 units on the x-axis and 1, 2, 3 units on the y-axis. Okay. Okay, so setting up our double integral, integral of that thing with respect to x is going to be 3x squared plus 8, and then minus the integral of this thing with respect to y, so that'd be 3x squared, and then d whatever, right, dA. Okay, so that's just going to be the double integral of 8 dA. If you factor out the 8, that's just the area of this slice, you know. So the area of that thing is just the area of the ellipse minus the area of the circle. So this will be 8 times the area of the ellipse, I said earlier, is pi times the two different radii, so 3 times 4, minus the area of the circle, which is pi r squared, so 4 pi. So you get 12 minus 4 is 8. 8 times 8 is 64, and pi, and then you're done. Okay, as usual, thank you for watching, and I will see you next time.